Good afternoon. It's an honor for me to be with you today, and I would like to thank SPRi to organize such a wonderful platform to share information. In my speech, I will talk about the nature of software-related failures and how we assign software criticalities and why it is important. So in this room, how many people believe in that software can cause or kill somebody? Just raise your hand. If you believe that software can kill somebody, all right, so we need to convince some people. We are not on the same page right now, but we will be on the same airplane at the end of that presentation. Okay, the question is, software can cause death or loss of property? Yes, definitely software can cause all those. Software looks innocent, right? We cannot see, touch software. But software integrated into a critical systems and equipment, and operation of that equipment can cause safety concern. You may remember Mars Polar Lander accident in 1999, right? So onboard software mistook the jolt, the vibration on, mistook the jolt of landing leg deployment as ground contact. Software shut down the engines. Like rocket were supposed to continue until one of the landing leg touches the ground Mars surface, but software did it earlier and caused loss of Mars Polar Lander after years research. And another incident on Boeing 777, right, in 2005. Pilot got misleading information. High speed, low speed, stall speed. Aircraft was approaching to stall speed, and stick shaker activated, right? Pilot disengaged the autopilot and back to airport with the guidance of radar and air traffic management. What was wrong in this case? Software again, right? Latent software error in ADRI, Air Data Inertial Reference Unit. Investigation reports, just very detailed reports, you should check that. And latent software error, ADRI is sending the information, flight critical information to the primary computer. And then the accelerometer provides data to ADRI. 4 years before the incident, one of the accelerometer, number 5, failed, but software disregarded that accelerometer erroneous data. And at the time of the incident, in 2005, another accelerometer, number 6, failed. In this case, software used previously failed accelerometer data, which was erroneous, mislead the pilot. So in 10 years, between 1988 till 1998, in 10 years, more than 300 accidents and incidents reported because of the erroneous flight deck information. So software is critical, right? Everybody now thinking software doesn't kill anybody? We'll see soon. So we are talking about software safety, hardware safety. What is safety? We should understand first what is safety. Safety is freedom from any condition that can cause death, injury, loss of equipment, property, environmental harm. Another definition is the state in which risk is acceptable. Now we start talking about risk. And a question comes up, what is risk? Risk is a probability of any occurrence and associated level of severity, right? We know if we kill someone, it's catastrophic. If we lose aircraft, it is catastrophic. And the probability is, if the probability is high, risk is high. But in terms of software, can we use that risk matrix really? Okay, we know software can cause that severe effect. But really probability point of view, how we can evaluate software, how we can calculate failure rate or reliability, it is really difficult to do that. So we cannot use that concept when it comes to software safety. Now I will convince you, because not everybody just raised their hand when I asked that question. Let's see and how software can cause. Here is just imagine a high-speed train or aircraft at the top, an accident. Now we just start from here, step by step, going through. A fault, just faulty code you may design in your software, right? Imagine that 5 plus 4 equals 8 instead of 9. Software now generating wrong data, right, because of faulty equation. And then it become error because you generate wrong information here. And do you think error can lead a failure? It depends. Maybe or may not be. So failure is more equipment-centric. Software operates in a computer, like primary flight computer. It's a critical computer. And if that data used in that computer, and then if that data is performing a critical function, then it creates failure, because that computer sent the erroneous data to upper level, autopilot, for example, right? When you are taking takeoff mode, and autopilot command the flight control service and roll and crash. Here is, we got accident. So now asking the same question again, do you believe that software can cause that? Please raise your hand. Okay, we got some couple people to convince. All right, as Amir told that software nature is different. Software failures are systematic. Whenever set of conditions happen, always we got the same output. Whenever we execute that faulty code in software, it generates erroneous failure. So we need to follow a process-based approach. I don't want to talk about that. Emmer talked about that random failures. It's easy for us as engineers to manage that side. Now, today's topic is cyber-physical systems. Critical cyber-physical systems and complex cyber-physical systems in any industries. For medical device, we don't want to kill a patient because of the overdose of radiation, right? We don't want, we are just nicely dressed and singing in our car. We don't want airbag inadvertently deployed, right? Killed us. But we definitely want it when needed, right? And in railway, in train, metro train, we don't want the sliding door open during the train is in movement. We don't want that in our life. So it's really important things. Think about that. And guess what? It's good news for you. Engineers are responsible for safety of that product, right? Because engineers have close proximity to design, implementation, and testing, and they are the first to identify failures and mitigate that. Now we are talking about cyber-physical systems. What is cyber? It's a very popular name, cyber-physical. Software, hardware, human, network, all interacting to each other, right? So I design a system. I know it is very safe. I use all techniques, but I am as safe as my weakest point. If I get any data from a drone, and if data sent my system to erroneously, and my system will fail. So when we look cyber-physical systems, we need to assess interactions too, not only the individual systems. So safety assessment of those interactions and systems becoming more critical nowadays. So we understand that software failures is systematic. Whenever set of conditions satisfies, we get the wrong information from software. So how we can mitigate error in software design, requirements, and integration? So we need to use different techniques. We call it development assurance process. Step-by-step process, we follow a process, robust process. And how we can identify how much development assurance rigor we should pay for our software. Not every software is critical, but some software is catastrophic. So first, we need to identify the criticality levels and then put the sufficient rigor, development assurance rigor, to develop our critical software. Also, it is cost effective. If we identified which software is critical, we pay more attention. Some software has no safety effect. We don't need to pay that rigorous process or to develop that kind of software. Now, here is some standards. So you know now, Amir talked about that standards, functional safety. In automotive industry, we use ISO. It's based on that standards, but describe integrity level from D to A. D is highest level. The idea is the same, but terminology is different in different industry and standards. And in military program, it's a popular standard. We use military standard 882. It's called software control category. In aviation, you know, level A, level B softwares, DO178, criticalities, coming from those guidelines. We use ARP 4754A and 4761. Now, today, I will talk about aviation best practice. Here is a connection: system safety, safety assessment, fault trees, functional hazard assessment identified by these guidelines. And system development process, aircraft and system development process, software development lifecycle, DO178, and complex hardware development lifecycle, DO254. You know that. Every guidelines and standards has V-chart, validation and verification, popular system engineering chart. But I like that chart much better than the other standards. Why? Because it defines safety and development process very well. Safety assessment in every stage. Don't bother, but software is here. Software design looks a little bit of that whole development cycle, but it's big effect on all of the safety. Now for aircraft, you can put here a medical device, a train, or whatever safety critical system at top. Now, aircraft function, functional hazard assessment, functional requirements, aircraft architecture, safety assessment of that architecture, aircraft systems, functions, functional hazard assessment. You see assessment, safety assessment in those development life cycle and just back and forth, it generates the derived safety requirements. Development assurance level and criticality flows down to software. Software cannot determine that because the function of software depends on the systems. Like it's application specific. If I use software on my laptop, not critical, but the same software on aircraft, it's critical. The platform is important. We assign requirements, flow down to requirements, and trace back. It's important to trace back to requirements to system and aircraft. Now we are here, software design, millions of codes, so open to fault and error, right? So can we really mitigate all error? We should do our best to do that, right? Test, review, analysis of requirements here, software design. And what happens if we miss error and fault in our software design? We integrate that software to item, and integrate that item to a system, integrate that system on aircraft. Our fault goes to aircraft with that. Like remember Boeing 777? That ADRI fault was in certification process. When the ADRI is certified by authorities, that latent failure was in there. And after years later, that creates problem. So those kind of errors, systematic errors, goes up to aircraft and someday can create hazard for every critical systems. Now, we said that development error should be mitigated in design and requirements and integration, we need to follow a process. We call it development assurance process, step-by-step process, planning, requirement capture, validation, verification, traceability, test, analysis, configuration management, process assurance, all is the process-based approach to mitigate systematic failure in design. In aviation, we got 2 different development assurance level assignment in the best practice guidelines. So one is FDAL, Functional Development Assurance Level, assigned to function. Since functional requirements, software do functional requirements, so many requirements, functional requirements. So we need to identify the function criticality first. And IDAL, Item Development Assurance, assigned to hardware and software. This is more function and system level. This is hardware and software level. In aviation, we got 5 levels from A to E. In the other standards functional safety, they use numbers. And ISO use D to A. I mean, the different terminology, but the idea is the same, mitigate those systematic errors and failures in the design. So we do functional hazard assessment. We know our function. To design, start with functional development, right? And then we assess function. What if we lose function? What if erroneous functioning? The effect of that functional failures create some catastrophe, some hazardous effect, some major effect on aircraft level. So we assign A, B, C, D, and E. Remember that table. We will just do some examples, simple example to assign criticality. And we can use another table. If we just get credit of our architecture, we can use that table too. Just imagine that there's a function performed by 2 independent systems, right? So in this case, as long as we show the independency, we can use options here in this table. Like, you know, our system is critical. We assign level A, and we assign 2 systems, level A and C, or 2 Bs for systems. In a short time, I will explain with a simple example. But before to start to identify how we can determine criticality level, we need to ask the right question as safety engineers. What does system do? This is the first question we should ask to each system. What can go wrong? What happens if it goes wrong? What can cause it to go wrong? What is the risk? Can we accept risk? Every engineer should ask those questions to themselves when they design their systems. What does it do question is a function of a system. For aircraft, the pitch control, that movement, up and down movement, is a function of aircraft. What if we lose that pitch control? This is a failure condition we should ask for each function. We lose aircraft. If we lose aircraft, it's a catastrophic consequences with that people. So functional hazard assessment is a very popular assessment to assess functional failures. So it can be performed at aircraft level or system level. So every industry uses that to determine the criticality levels of functions. We evaluate loss of functions, inadvertent operation of functions, erroneous operation of functions in functional hazard assessment. Now for aircraft, we look the effect on aircraft, effect on crew, effect on occupants. For train, we should do the same. For medical device, they evaluate different things, but effect on the patients, effect on the people, we should evaluate the effects of failure condition. And if we kill somebody, it is catastrophic. We should assign level A, the highest criticality. Now do some example together. Very simple example. Those are aircraft top-level functions. We need to evaluate each function of the aircraft. Just we need to pick one for an example. One function is to control speed. We need to stop aircraft when it lands. Let's do the example, functional hazard assessment. Our function is decelerate aircraft on ground. Right? What if we lose that deceleration during landing phase? You don't want to be on that aeroplane if you lose that function. So it is catastrophic, kill people because of high-speed overrun. Now, we know that function is critical, right? We assessed it in functional hazard assessment. We assign level A, right? And inadvertent deceleration, another failure case, we need to assess. And when it is important during takeoff phase, not landing this time, right? You are ready to take off. You come to V1, decision speed. After V1, you have to fly because you are in high speed. So what if inadvertently decelerate, systems inadvertently decelerate the aircraft? It leads catastrophic too because of high speed overrun again. Now we know that function is critical function, catastrophic function, and we assign level A. Keep it in mind, okay? We will go further right now. Now, we design our aircraft. It's a very simplified figure. And what kind of system providing that deceleration function is one is the engine, thrust reverse, and another one wheel brake. Landing gear open and stop the aircraft. Okay, we got two systems. Good. Are they independent? Yes, we did it. We are engineers, we are smart, we did independent systems. And go further, we did fault tree assessment to evaluate proposed architecture right now. Oh, and gate, independency. Fault tree says minimal cost says two independent functions here. Good, can I remember the other table? And I can assign one system A, the other one C, or two Bs, remember the options? It seems we can use that right now because it's two independent systems. But be careful before assigning assurance level, right? We have to evaluate every failure condition in our functional hazard assessment. Remember, inadvertent deceleration was catastrophic too. We identified it. And let's see our architecture, if our architecture is what it says us. And see here in our fault tree, it's an OR gate. Each single system leads inadvertent deceleration during takeoff, right? We cannot get credit from the architectural mitigations, right? So we have to assign both system level A in this case because both systems individually lead that catastrophic failure condition. Now we are sure that deceleration function is catastrophic, level A, and we are sure that wheel braking system is catastrophic. We assign now system level. Function A, system level A. Now we are going through the equipment and software in a short time. Here is our wheel brake system. We know that function is critical, level A. And in wheel brake systems, there is a computer, braking system control unit, right? It's a smart computer, commands brakes. Now, it's a safety process responsibility to assign software assurance level. And it depends on the software architecture. Are we using dissimilar different architecture, independence architecture in our software? If yes, we can get the credit from that architecture. In our example, our designer just made two independent command and monitor functions. Command and monitor software in this case. So we show independency by doing safety assessment, common mode. We look every common mode. We are sure that it is independent. Partition design, this similar software. We did everything. So now we know that we can assign two Bs, or we can assign command function level A and monitor function level C, or we can assign both functions, both software level B. Now, you know now that the software criticalities, DO-178 standards, you're familiar as software people, where it's come from. It's come from system level, aircraft level. It's come from safety assessment. After we assign that criticality, you start using those guidance to comply with the certification requirements. So in aviation, we use ARPs. It's a recommended practice to develop aircraft systems and equipment here. And when we assign criticality levels and software and hardware, DO-254 and DO-178C provide process assurance techniques and methods to develop software. So the last but not the least, I would like to remind you, Murphy is always right, isn't it? He says that if anything can go wrong, then it will be. In aviation version of that code, if something can be fitted incorrectly, then someone someday did it this way. So we need to be careful about human factor. Human make mistakes, and human mistakes is a systematic error that creates systematic error. And I would like to just one more quote from Albert Einstein. He said that the clever engineers solve the problem, clever person solve the problem, but wise person avoid it. Please be wise engineer, right? Don't just spend more time to solving problem. All safety assessment, why we are here, to just avoid problem failures, to make the environment safer. 감사합니다. Thank you very much.